Hi friends, today we will see the pictorial representation of a scaling, right? And we have discussed in the last lecture. Scaling is represented mathematically as x of at. A can be greater than 1 or it can be less than 1. When a is greater than 1, it is nothing but compression. When a is less than 1, it is nothing but expansion. Okay? So, we will see the pictorial representation when assuming a is greater than 1. We will see pictorially when a is greater than 1 how this is called a compression in time domain. When a is less than 1, why this is called as expansion in time domain. Okay. Now let's assume that a signal x of t where t is the independent variable. If I scale this independent variable by some constant, say a, what I get is x of at. Just replace the independent variable t by some constant. Independent variable, you have to scale it. Independent variable, we have to scale it by a constant a. Then what we get is a scaled signal. Okay. Now x of t is defined. Here the independent variable is varying from minus infinity to plus infinity. X of t is defined from between the intervals minus 1 to plus 1. Because I know that x of t, here x of t is having the increasing slope. Here x of t is having a decreasing slope. Right? So this x of t is defined, or this is not equal to 0 for t greater than minus 1 and less than 1. In between these two intervals, x of t is defined. I'm not writing a mathematical expression for increasing slope and decreasing slope. I'm just writing x of t as it is defined, or this is not equal to 0 for t greater than minus 1 and less than 1. And for rest other values of t, x of t equal to 0. Why? Because for t greater than 1, x of t is 0. For t less than minus 1, here you can see here when t is varying from minus infinity to minus 1, x of t is 0. So I just define x of t as x of t is not equal to 0 for t greater than minus 1 less than 1, and this is equal to 0 otherwise. Now we discussed a can be greater than 1, it can be less than 1. When a is greater than 1, we call this as compression. Why we are saying it as a compression? We will see that with a pictorial representation, pictorial representation. Okay, when a is greater than 1, x of t is defined, or this is not equal to 0 for t greater than minus 1 and less than 1. Now what I want is, for compression, a is greater than 1. So assume a equal to 2. 2 is greater than 1. Right? So now x of at, we have a signal x of at. It's nothing but a is replaced by 2. This is nothing but x of 2t. X of 2t. Just replace the independent variable. Just replace the independent variable t by 2t to get a signal x of 2t. That's it. So now I can write x of 2t as, just replace wherever you find the independent variable, just replace the independent variable by 2t. So here now we can see here we find the independent variable t. So I'll just replace this expression x of t is defined or not equal to 0 for 2t greater than minus 1 less than 1. That is the definition of x of 2t. Defined or not equal to 0 for t, 2t. I just replace the independent variable by 2t greater than minus 1 less than 1. So I can write x of 2t is defined or not equal to 0 for minus 1 by 2 less than t less than 1 by 2. Right? So this x of 2t is defined for t greater than minus 1 by 2 and less than 1 by 2, and this is equal to 0 otherwise. Why? Why? Because x of t equal to 0 for any value of t which is not in between the intervals minus 1 and plus 1. Similarly, x of 2t equal to 0, which is not in between the values minus 1 by 2 to plus 1 by 2. So now I can have diagrammatical representation of x of 2t. Now we will see the diagrammatical representation of x of 2t. This x of 2t is defined or not equal to 0 for t greater than minus 1 by 2 to plus 1 by 2. So here this is 1, this is minus 1, this is plus 1. I'll find minus 1 by 2 to plus 1 by 2 here. So this x of 2t is nothing but x of 2t. This x of 2t is defined or not equal to 0. Now what observations we find from both of this x of t and x of 2t? What observations do we find from both of these diagrams, x of t and x of 2t? Now we can see the shape of the signal, x of t, whatever the shape of a signal, the shape of the signal is maintained here, right? The shape, increasing slope, decreasing slope, increasing slope, decreasing slope has been maintained. The only difference is here t is varying from minus 1 by 2 to plus 1. Here t is varying from minus 1 to plus 1. That is, x of t is defined in between these intervals. X of 2t is defined only between the intervals minus 1 by 2 to plus 1 by 2. Now, if I do a compression in time, if I compress this time, what I get is x of 2t. So, this I call it as compression. Compression in what? In time domain, because if I compress the signal in time domain only, we will get this x of 2t. Compression in time domain. Compression in time domain. Now we will see what is expansion in the time domain. Right? We will see the expansion in time domain. For expansion in time domain, all we need is a is less than 1. So we will see expansion. Expansion in time domain. For expansion in time domain, I am assuming a is less than 1. When a equal to 1 by 2, assuming a equal to 1 by 2, which is less than 1. So, x of at is equal to x of 1 by 2 into t, which is equal to x of t by 2, right? Now, I'll write an expression for x of t by 2. X of t by 2 is nothing but wherever you find an independent variable, just this expression follows. But only changes wherever you find an independent variable, just replace it by 1 by t by 2. Wherever you find an independent variable, just replace it by t by 2. So, x of t by 2 is defined or not equal to 0. I'm just writing this expression. Only the independent variable t here changes to t by 2. Why? Because I'm scaling it by some constant, which is 1 by 2 less than 1. This x of t by 2 is defined for t by 2 less than minus 1 less than 1. And this is equal to 0 otherwise. Right? So now I can write x of t by 2 is equal to r. This is not equal to 0 for t greater than minus 2 less than 1. X of t is not equal to 0 for t greater than minus 2 less than 1. This is equal to 0 otherwise. So this is 2 otherwise. So now I have a signal x of t which is varying from minus 1 to plus 1. Now x of t by 2 is the same signal, the shape of the signal will be same. X of t by 2, the shape of x of t by 2 is same as x of t, but only changes t is varying from minus 2 to plus 2 instead of minus 1 to plus 1. So what I get is t is varying from minus 2 to plus 2. This is x of 2t. If I stretch the signal in time domain, what I get is x of 2t. So this is nothing but expansion in time domain. Expansion in time domain. In the next lecture, we will see shifting property as well as time reversal property, diagrammatical representation of shifting as well as time reversal. Thank you.